In example 3, we are supposed to prove that the set of integers is isomorphic to the group of even integers under addition. So integers under addition, even integers under addition. We want to show that those two groups are isomorphic. How do you show that two things are isomorphic? Well, one way to show it is to find the isomorphism and to show that it actually is an isomorphism. So that's what we need to do. Let me write that down. So what do we need to do? We need to find an isomorphism. From one to the other, from Z to E, and show that it is an isomorphism. And how do you show that something is an isomorphism? If you go back to the definition, there are three things that we need to do. An isomorphism is one-to-one. An isomorphism has to be onto. And it has to preserve the operation. It's operation preserving. I hope you can still read that. So those are the three things we need to show. So we have four things to do here. We have to find an isomorphism, and then once we have them, the isomorphism, then we have to show that it's one-to-one, onto, and that it preserves the operation. All right, so what would be the isomorphism? You may want to pause and think about it a little bit. One way that you can start thinking about it is we can write down the integers. So let's write down the integers 0, 1, 2, 3, and so on. And then we also need to go in the negative direction, -1, -2, -3. And where do you want to send all those things? So 0, where should that go? 1, where should that go? 2, where should that go? So we want to go from the integers in a one-to-one and onto way to the set of even integers. One way you can do that, I hope you've thought about it for a little bit. You could send 0 to itself, and then you could send, where could we send 1? We could send it to 2. What about 2? We could send it to 4, and 3 we could send it to 6. And then -1 we could send to -2. -2 we could send to -4, and -3 we could send to -6. And this scheme would work. I hope you see the pattern here. So how do we describe this? It would be nice to have a formula that we can work with. So we can define phi to go from Z to E by saying where we are sending an arbitrary element. So the integer m is sent to 2m. And that is our isomorphism. So this is our isomorphism. So we found one, but we haven't shown yet that it is an isomorphism. We just defined it. Okay. So now we need to prove that it actually is an isomorphism. So the first thing we need to do is to show that it's one-to-one. And this is something that works here exactly the same way that it worked in your proof writing class, and that it worked in that it's working in real analysis. So how do you show that something is one-to-one? You suppose that two outputs are the same, and then you show that if two outputs are the same, they have to come from the same inputs. So let's suppose phi of m is equal to phi of n for some m and n in Z. Okay. Then what do we know? Then what is phi of m? That is 2m. And phi of n, that's 2n. So then we have that 2m is equal to 2n, but that means that m is equal to n. So this part is really short, which then shows that phi is 1-to-1. So we're done with the 1-to-1 part. What about with the onto part? How do you show that a function is onto? Well, you have to pick something in your codomain. So we have to pick something in E. Let's call it K. And then you have to demonstrate that the isomorphism will definitely hit that element that we just chose. So where does it come from? Well, if K is in E, that means it's even. But if it's even, then we have to write it as 2 times something. So there exists an m in Z such that K is equal to 2m. Well, but there's our candidate for the input that gets sent to K. It's m. So we have that phi of m is equal to 2m, which is equal to K. So that means that phi maps onto E. So it's onto. Okay, it's 1-to-1, it's onto. Last thing, does it preserve the operation? So is it operation preserving? Okay, for that we have to choose any 2 elements in Z and then apply do the group action in Z, apply phi, compare what happens if we first apply phi and then apply the group action. So choose any m and n in Z. Okay, so then what do we have? So if we look at phi of m plus n, so remember addition is our group operation right here, then what is that? So we apply phi to the element m plus n, which is in Z. Well, m plus n is in Z. Phi sends m plus n to 2 times whatever m plus n was. So this is what we have. But 2 times m plus n is 2 times m plus 2 times n, because we are in the world of integers right here. And that is the definition of phi of m plus phi of n. So we see that our operation phi, our isomorphism phi, preserves our operation. And thus we have shown that phi is in fact an isomorphism. And since we were able to define an isomorphism from our group Z to our group E, it follows that Z is isomorphic to E. So the integers have the same structure, are more or less identical as far as algebra is concerned as a set of even integers. Surprised? Maybe you already looked at this in real analysis too, but there you will look at the size of both of those sets and you will pretty much come up with the same conclusion, that there is not a big difference between the set of integers and the set of even integers.